Have you ever wondered how scientists predict the cooling of a cup of coffee or the growth of a population? These real-world phenomena are described by differential equations. Today, we will master the most fundamental technique for solving them, the method of separation of variables. This elegant approach allows us to break down complex rates of change into simple, solvable integrals. Consider a population where the rate of growth is proportional to the current size. This relationship is expressed as dp over dt equals k times p. To find the actual population at any time, we need to solve for p. This is a first-order differential equation because it involves the first derivative, and it is the perfect candidate for separation. Our objective is to move from an equation containing derivatives back to a general solution, a function that satisfies the relationship. By the end of this lesson, you will be able to identify, rearrange, and integrate these equations to uncover the hidden functions that govern dynamic systems. Before we dive in, remember that integration is the inverse of differentiation. Specifically, separation of variables is essentially the chain rule in reverse. You should be comfortable with basic integration rules, such as the power rule and the natural log rule, as these will be our primary tools for solving the resulting expressions. It is also helpful to view dy over dx not just as a single symbol, but as a ratio of differentials. In separable equations, we treat dy and dx as independent pieces that we can algebraically move to opposite sides of the equation. This algebraic manipulation is the separation that makes the method work. A first-order differential equation is called separable if the derivative can be expressed as a product of two functions, one strictly of x and one strictly of y. If you can write the equation in the form dy over dx equals g of x times h of y, you are ready to separate and solve. The first step is to rearrange the equation so that all terms involving y are on the side with dy, and all terms involving x are on the side with dx. We do this by dividing both sides by h of y and multiplying both sides by dx. Now, the variables are completely isolated from one another. Once separated, we apply the integral sign to both sides. We integrate the left side with respect to y and the right side with respect to x. Note that while both sides technically produce a constant of integration, we typically combine them into a single constant, usually labeled c, on the side of the independent variable. The result of our integration is the general solution, representing a whole family of curves. If we are given an initial condition, a specific point that the function must pass through, we can solve for the constant c to find the particular solution. This represents the specific scenario we are modeling. Think of a differential equation as a map of slopes. At every point x, y, the equation dy over dx tells you which way to go. Solving the equation is like drawing a path that follows those arrows perfectly. Separation of variables is just the algebraic way to find the equation for that path. Let's work through an example. Suppose dy over dx equals 2x divided by y. To separate the variables, we multiply both sides by y and by dx. This gives us y times dy on the left and 2x times dx on the right. The variables are now successfully separated. Next, we integrate. The integral of y with respect to y is 1/2 y squared. The integral of 2x with respect to x is x squared. We add our constant c to the right side. This is called an implicit solution because y is not yet isolated. It defines a relationship between x and y. To find the explicit solution, we multiply by 2 and take the square root. Note that 2 times c is still just a constant, which we can rename k for simplicity. Our final general solution is y equals plus or minus the square root of 2x squared plus k. This represents a family of hyperbolas. Let's try one with an initial condition. Given dy over dx equals negative x times y, with y of 0 equaling 3. First, separate, divide by y and multiply by dx. We get 1 over y dy equals negative x dx. Now we are ready to integrate both sides. The integral of 1 over y is the natural log of the absolute value of y. On the right, we get negative 1/2 x squared plus c. To solve for y, we exponentiate both sides. This gives us y equals e to the power of negative 1/2 x squared plus c, which can be rewritten as y equals a times e to the negative 1/2 x squared. Now we apply our initial condition, when x is 0, y is 3. Plugging these in, we find that a must be 3. Our particular solution is y equals 3 times e to the power of negative 1/2 x squared. This specific curve describes the exact behavior of our system starting from our initial point. The most famous separable equation is dy over dt equals k times y. This describes any system where growth depends on the current amount. Using our method, we find the solution is y equals c times e to the kt. This is the formula for continuous interest and unrestricted biological growth. Another application is Newton's law of cooling. The rate of change of temperature T is proportional to the difference between the object and its surroundings. By treating T minus tar as a single block, we can separate the variables and solve for how an object reaches thermal equilibrium. Be careful! When we divide by h of y, we assume that h of y is not 0. Sometimes, the constant function where h of y equals 0 is actually a valid solution that we might lose during the division process. These are called singular solutions and should always be checked separately. Not every differential equation is separable. For example, dy over dx equals x plus y cannot be factored into a product of x and y functions. For these, we need other techniques like integrating factors. Always check for factorability before you start the separation process. The most common mistake is forgetting the constant of integration, c. Without c, you only have one curve instead of the entire family of possible solutions. Always add c the moment you perform the integration, especially before you start solving for y algebraically. Watch your algebra when exponentiating. If you have the natural log of y equals x plus c, then y equals e to the power of the entire side, x plus c. This simplifies to a constant a times e to the x, not e to the x plus a constant. Small algebraic slips can lead to very different functions. Sometimes an equation doesn't look separable at first glance. If you see dy over dx equals x plus x times y, you must factor out the x to see the product. If you try to move terms without factoring, you will get stuck with a dx term attached to a y, making integration impossible. To summarize, solving separable equations follows a clear four-step path. First, algebraically separate the variables. Second, integrate both sides. Third, ensure you include the constant of integration. Finally, if required, solve for y to get an explicit function. This process turns calculus into a powerful predictive tool. Here is a quick challenge: solve dy over dx equals 3x squared with the initial condition y of 0 equals 1. By separating and integrating, you find y equals x cubed plus c. Plugging in the point 0, 1 gives us c equals 1. Thank you for learning with us today. Generated by Vision Solve AI.